So starts with the conductor. The material which allow the electric current to the pass through them is called conductor. Insulator, the material which do not conduct the electric current to passes through them is called insulator. And semiconductor, the material which partially conduct electricity is called semiconductor. They have conductance and resistivity between the conductor or the insulator. So in my previous video we had already discussed about the conductor, insulator or semiconductor, their major differences or other things. So with the help of energy diagram or a Venn diagram. So now in today's video we are going to discuss the types of the semiconductor. So let's start. There are two types of semiconductor. First one is intrinsic and second one is extrinsic. So what is intrinsic? Intrinsic semiconductor, poor semiconductor without any impurities. They are the compound or a one kind of material like silicon or a germanium. So it was undoped and type first. When T is equals to 0, conductivity is 0, temperature, and when a temperature increases, conductivity increases. Free electron are due to the natural cause. Number of holes and electron determine the property of itself instead of impurities. Number of electron is equals to number of holes. As we know in the energy diagram, this one is valence band and this one is conduction band. So here is holes and there is electron. This one is called holes and this one is electron. Number of electron and in a conduction band depends on the temperature and the magnitude of the band gap. Band structure of the silicon. In the quantum mechanics, the fact that the crystal structure of the silicon is quite different from the sodium. The structure of sodium is with the BCC with CN4, while silicon is FCC. This one is in a solid. You have already discussed about the phase centric, cubic centric. So this one is FCC, BCC, and the CN coordination number is 4. However, the non-mathematical explanation of the band structure of Si may give starts from the assumption that silicon forms 4 equal bonds then arranged tetrahedrally and regards with the sp3 hybridized. Each hybrid orbital will overlap the adjacent silicon to form the molecular orbital from 1 sigma to sigma star. Sigma became valence band, where sigma became valence band and sigma star became conduction band. And the conduction band is empty. Mechanism, we know that the electronic configuration of the element having 4 electrons in their outermost and the valence as the temperature increases, the gain of the electron more than thermal energy break the bond and became free. The process of the ionization of the atom in the crystal lattice creates the valency in the bond between the atom, the position from which the electron get dislocated in the hole in which the equivalent to the effective position of the positive charge. The hole is then occupied by the free electron. So here you can see this one positive charge is hole and this one is electron. So the electron is occupies in it in a hole. So here this is our ongoing. The hole is occupied by the free electron as result in which the latter vacant. So where the position just like here the electron exists, they completed this hole, but this place was vacant. By the filling this position became a hole and became a neutral position. At the temperature 0 Kelvin, intrinsic semiconductor behave like an insulator. At the temperature increases, electron excited from valence to conduction band. The electron occupied in the conduction band partially leaving the corresponding equal number of hole in the valence band, as you can see that 1s2, 2s2, 2p6, 3s2 and 3p2. So here is the structure of the silicon. So here here you can see this is a free electron and this one is hole. This completed this and making like a vacant space here. Extrinsic, there is found by the doping of some semiconductor with a certain specific impurity amount. Impure and doped semiconductor. Extrinsic semiconductor, no density of electron in a hole Electrically conductivity is high. Property of semiconductor depend on the impurity in which doped. The process of the adding impurity is called doping, and the atom which are used to impurity modified their the electrical property of the semiconductor. So here is also two type, pentavalent or a trivalent. So here you can see tetravalent, pentavalent. This one is trivalent and this one is pentavalent. So let's start with the p-type semiconductor. As we know that the pure intrinsic silicon semiconductor in a nucleus use four valence electron or a four valence bond, which is neighbor. Each ionic core consisting of the nucleus of the non-valent electron has a net charge of plus positive and surrounded by the four valence electron. Since there is a no excess electron and hole for the conductivity, and there is electron, the hole are equal. Now if the atom in the semiconductor lattice is replaced by the element with 3 electron in the group, boron, germanium, the impurity will contribute 3 electrovolt to a lattice, leaving one excess hole. The hole is except if electron which is responsible for the conductivity of extrinsic semiconductor. So this one is called group 3 impurity is called acceptor because of the acceptor donate excess of the hole is considered as positive, or doped acceptor is called p-type semiconductor. Here you can see this one is Venn diagram for the p-type semiconductor. Whereas n-type semiconductor, in the addition of the replacement of the lattice atom 5 electron volt, same as previous, but here is a 5 electron volt. In the case of impurity, 5 added at 5 valence electron lattice had only 4, means one excessive electron form. This is donor. P type is acceptor and this type is donor. Majority electron, minority hole. Here you can easily see the Venn diagram. So thanks for watching.